Okay, hello everyone. Today I'm gonna teach you something about subroutines, how to link different subroutines to each other, how to make them to transfer data. And for example, in this very specific subroutine, I have a UMAT, which is gonna simulate elastic plastic deformation for me. And I'm gonna have it linked with a freak subroutine for friction. I'm using this freak subroutine because point is in Abaqus, as you know, if you go over here in interaction module and in the property, as you see, for tangential behavior, if you put it for as penalty, then you just can have one ultimate elastic strain or shear yield strains for entire contact surface. So if I want to have it uh, as a function of yield strengths, for example, at different points I want to have different ultimate shear stress, I cannot use this option. So, and point is why the reason that I have decided to work on this one for you is because if you know, in Freak we have a node over here, which means the data are gonna be defined in at contact nodes over the slave surface. But in UMAT we have again this node over here, uh, and we have NOEL here, which means that the data are given for elements or integration points. So not only I'm going to teach you how to make the subroutines to transfer data between each other, but I'm going to show you as an example how to link UMAT and Freak, uh, or in other words, how to get the data from integration points and transfer them to another subroutine, which is Freak subroutine, and interpret those data as data for nodes. This is a freak subroutine. So at first, let me walk you through the model that we're gonna work on. This is the axisymmetric model, and this is a quarter of the geometry, and this is one part, and this is another part, and uh, there is a contact between them. If I go to this contact module, we will see this contact surface. So this will be a slave. The surface from this part will be a slave, and the surface from this part will be the master. And I have it meshed something like this. So as you see, the slave is meshed with a more refined element. And so I have defined this contact, and for contact properties, I have it to use uh, user define, which will be the freak and subroutine that we're going to use with, and I have this friction property, which will give me the friction coefficient equal to 0.1. Okay, let's get started with going through the subroutine. I'm not gonna talk about the subroutines, not UMAT and not freak. I'm just gonna tell you how to link them and how to transfer data between them. There are so many different ways that you can use to transfer data between different subroutines. For example, one of them is just something like this. You are in one of the subroutines, for example, you are in UMAT, and you want to use another subroutine. And for example, here I have defined a subroutine, which is KMLT, and just for your information, this is something that will multiply this tensor and this tensor and will give me this tensor as a result. So I will use this call function to call this subroutine within another subroutine, and this will be the data that I will put I will give to this subroutine as input, and this will be the output of this subroutine. So over here, up to this point, I will define these two tensors, and when I put them here, they will be inputted to this subroutine, and the result of this call will be a FUU. So before coming to this point, I know these two part, and after this line, after this KMLT being called, I know FUU. But what is this KMLT? Let me split the window to have them both at the same time over here, and let me find this subroutine. I think it should be down here. It's a pretty long subroutine, and okay, this is a subroutine that I have it here. Okay, point is, if you want to use a subroutine in middle of another subroutine, the main subroutine, which will be this one, will be placed upper than this one. So for example, you see this is in line 94, which is in the middle of the main subroutine, or UMAT the subroutine, and this is the subroutine that it is called over there, and it is in line 1300, which means that it is after this main subroutine. So for example, here, if I have another subroutine, just let me show you another subroutine. For example, I have another subroutine here, and this subroutine, because it is in the middle of the UMAT one, it should be placed after UMAT subroutine. Okay, so we are talking about this subroutine KMLT. As I just said, these two are inputs, and this is output. So if you go over here, I have this original general name DM1, DM2, and DM. So DM, when you call this one, this first term will be assigned to this one, DM boy, and this one, X stress, will be assigned to DM2. And the DM, which will be determined here, as you see over here, DM is the output of this, or resultant of this calculation. And the DM will be calculated and will be put over here. And because it is related to, for example, in this one, it is related to FSTR1, after this subroutine being called, I will have this one as input, this one as input, and I will have this one as output. This is one of the simplest way that you can link different subroutines to each other. For example, if I needed something else over here, I just could add any other terms here and have it what I want to have, input anything that I wanted to this KMLT subroutine over here. The other way that you can link subroutines to each other is using uh, a program. Uh, okay, the second way that you can link different subroutines with each other is, as I said, is using functions or programs or subprograms or external. You can call them whatever you wish. So for example, I'm here in the middle of a subroutine. For example, this is the main subroutine that I'm working with. And here I'm going to use a program that will determine something for me. And this program is called GSLP0. And when you are going to call or use a function in the middle of something, some other subroutine, you need to give it some some identification. So it is external, and which means that I'm going to use this subprogram or function. And what this function does is, if you go over here, this is the function that I'm going to use as you see this placed after this main one. This function gives these numbers as input and gives one single number as output. So for example, here GSLP is called in this subroutine as something like this. So, which means that I will have these numbers as input, and from all these inputs, it will calculate something, and it will give it to me as this number. So, for example, I have different numbers for each of one of these, and the result, there will be some calculation between of anything, and the result of this calculation between these inputs will be a number or a component which will be called over here, and you can place it in any format, any matrices or any arrays that you want. So as you see, the main difference here between the function and calling a subroutine, you see over here I have an entire matrix formed out of this subroutine being called, but over here I just have a number. Then I need to put it into matrices or different formats that I want to use. But this one is sometimes more convenient to use compared to this one. It is up to you. In different situations, you need to decide what you want to do. This is the second. It was the second way to link different subroutines to each other. But the very last one that I want to talk about this time, there are so many other ways that I want to talk about is using modules. Modules is somehow an advanced or much easier or better and uh, with better performance compared to common blocks. So in a few years back, for linking subroutines to each other, we used to use common files, common blocks. But recently, we have come to this conclusion that common blocks are not well enough, and sometimes just using them causes some divergence or problem in reaching a convergence. And sometimes the data are getting somehow messed up. But modules, I've never had any problem with modules. They are very easy to use, and they are always accurate. And I've never had any problem with this one in terms of having a slow convergence rate. So here, at first, let me walk you through how I'm gonna link UMAT and Freak, or in other words, how I'm gonna get the data from integration points and link them, relate them to nodal points. Then, when I am done with that, I will go through this part, how to use module. Okay, so let me open up the INP file that we're gonna use. This is the INP file that I will be using, and as you see, we have here the nodes, and after that elements, and if you define any sets or anything, it will be included over this part. The thing that I have done here is I I have defined a set over here, contact, by the name of contact. It is this contact surface, slave contact surface. Why I've done this is this because when I go to IMP file, I have a node set and element set of the nodes and elements which are in contact. Uh, the thing that I will be using will be this part. So these are the nodes, or if I go over here, these are the node numbers are every one of these nodes in contact on the slave service. And we also in this part at just right on top of it, we have elements which are giving me the element number and 4 nodes that are connected with that element. So this is because I'm using 4 node elements. And so if I find, so I have node numbers, I can find based on those node numbers, I can find elements which are connected to that node. So if I show it on picture over here, for example, I know the node number over for this node. Then based on using this file, which gives me the connectivity of elements, I can find this element and this element. So I have the node number, I know this number, the node number over here, and this number will be one of these 4 numbers for one of these elements. And if I find that, I will find these 2 elements connected to this node. So finally, what I'm going to do is finding any 2 elements which are connected to any desired node, and find the property of each of these elements, and somehow, for example, average these 2 numbers and relate that number to this node over here. For example, I want to determine the yield strength over this element and this element, and then I will average these 2 and assign it to yield strengths at this point. And I will use these yield strengths for the contact formulation. So what I need to do is I need to open up the IMP file. You can use different software. For example, you can use MATLAB, and you can write a simple code in it and just copy paste these elements and nodes and that contact nodes, and write a simple code to form the connectivity matrix. And by connectivity matrix, I need something. The result of this code should be something like this. That gives me, for example, this is the node number, and these are 2 elements that are linked to that number. And for example, this one is 0 because this is the very first point at the corner. This is this node over here, and because I just need because it has just 1 element, the other element number is 0. But other than that, all the elements, they have all the nodes, they are connected to 2 elements. So this is what I need to get from any code that you can write in any different desired software. For example, but here, to walk you through different abilities of using different softwares, different subroutines, I'm going to use I'm going to do this and derivation of this connectivity matrix, which again I need to show it to you. This matrix, connectivity matrix, I'm going to do it within UMAT subroutine. You can use different subroutines to determine it. For example, you can use USDFLD subroutine to determine it, or as like I said, you can just write a simple code in MATLAB or Mathematica or anything else and derive this matrix. But there are a lot of good things in doing it in UMAT. In terms of, there are a lot of things that we can learn here. For example, okay, at first, if I open up the IMP file, at first I'm going to go to search this IMP file and find this uh, nodes on contact surface, these nodes. But how I'm going to supposed to search within the IMP file, this is a cool way to do this. At first, uh, I will be okay. Let me find the proper position that I have it there, and okay, it is a long code, but it is okay. Yes, yeah, okay. there is a cool feature that we can just uh, point is, I don't know where it is positioned, but I just know that it is positioned below this line. So what I will do is I will define a search option, search item, better to say, and this search item is this one. And I have it, for example, here. And I know that these nodes, these sets of nodes will start at a line which starts with this one, and I have it here as a search item 3, and it ends over here, and I have this one, as you see over here, as search item 4. So what this code actually does is, let's start from here. I will go through the rest of the code in just a minute. I will open up the IMP file, and let's start with search 3 and 4 first. Okay, I will open the IMP file, and I will start reading the IMP file, and I had given it a large number, which should be a number that gives ends with this node, this point, but because I don't know what is the line number of this one, I've given a very large number. Then when I get to this point, I will cut the rest of the do loop. So I will read each line, and I will put each line into a phrase. And what the phrase is, I have defined the phrase over here, that over here a phrase can be 100 character lengths. So for example, I can 100 character lengths is sufficient to read all these long lines over here. If you have it, for example, if you know the length of the line, you can just put a definite number here. But if you don't know it, just give it a large number. And I've just given a large number, which is enough to have the entire row of elements over here. So it will read each line, which all these characters over here. Then it will try to see if this phrase matches with this search item. And search item is this for this case is search 3, which we defined it to be this one. So it will read it if this line, which is now is placed in this phrase, is equal to this search item. Then we know that we have got to the right point that we need to start collecting the data. So if we are at this point, okay, just exit the do loop, because now I know which line I need to start. So I know the start of this one. And then I need to find the end of this one again. So I will do the same thing, but I will start reading from I, which is when this reading is interrupted, which is at this point. And I will try give it. I have given it 1,000 because I just needed, I don't know, 20. Which over here I just had 11, 12 rows, so I just could have given it 12 rows, but I have given 1,000, which is fine because I'm gonna interrupt the do loop whenever I have what I want, what I'm looking for. So again, I will read each line and I will put it in a phrase, and when this phrase is equal to search for, which search for is this one, which is at the end of this numbers that I need, I will again interrupt it. But before, if this search is not equal to 1, because I know I'm within these numbers that I want to collect them, I will open another file in, for example, text in temp, and I have this number and name for it, contact nodes, and I will try to write them as an input file, output file. And so I will have this one, and it says, okay, we have not reached to this point, so I can write this one. Then it will go to another loop. It will write down another line. But when it gets to this point, it says, okay, now this phrase and search item are the same. So that's the point that I don't want to go any further, and I will erupt or exit this loop. So the result would be a file contact node, which will be something like this. And these numbers are exactly the same as these numbers. Um, This is a very simple and cool way how to get this done within the subroutine. But we have another step to go to work with these numbers. As you see, we have 16 characters, 16 numbers or items in line. And for example, here I have 12 rows of data. But point is, I need to know every single individual number. So I need to have, for example, this one as a, I need to, in other way, in other word, I need to put this matrix into an array, which gives me a better option to work with this number. So now I have a matrix which is 16 columns and 12 rows, but I'm gonna put it as one row and 16 by 11 rows. So what I want to do here, I will allocate. Why I've used allocate over here, because I didn't know how large these data are prior to reading them. So I have just read the data, and I know that I started at line. If you could follow me, we knew that the search item 3 started at line I, so we know the first one, and it interrupted, or we came out of the loop at line J. So we have I minus J, or J minus I lines between these two, and we know we have 16 characters over here. So altogether, we know how large this final file is gonna be. So I at first I have read this file again to put it into matrices. So this matrix will have 16 columns and j minus I minus 1 lines. I have excluded this one because I didn't want to include this part to make to cause some mess into the calculation. So I put it in a matrix which is co-node, and now using this co-node, I have reached to this final thing that I want, contact node, which will have one column, but it will have j minus I minus 1 multiplied by 16 characters. So now I know, now I have everything that I want, that I needed from nodes. It will be a single array. It is a matrix which has just one column. And I need to do the same to get all these element numbers. So I will have element number and all for connecting nodes. So for doing that, now it is easy and you know how to do it. But just to show you how to do it, so I know that elements will start at something like this. So I have this search phrase for the start of the search, and I know that this will end at the phrase something like this. So if I copy this one and search for it over here, this will be the end of this file that I need to read to have all elements and connecting nodes. So I have designed another loop to find the contact elements. And I have again opened up the INP file and found when this desired data will start and when they will end. And I have written a text for contact element. And the result of that is something like this, which again, if you check out, for example, the very last one, is as you see, this is the same. This is the element number, and these are the four contacting nodes, which are the same as the INP file. And I have it now here, so I can put it into any tensor matrix or anything other like that to form the connectivity. And okay, now I have uh, these two files. I have the this one, which now I have put it into a matrix which just has one column, and I have this connectivity, which means that I have element number and all connecting nodes. And so now I need to do a search and find, for example, for this node, I need to search which two elements they have used this node. For example, just to give an example, for example, for this node, I know that the element 4, and if I just search for it, I know that element number 4 and element number 320, they have used this one. So I just need to do this search over these nodes over here. So I've written a very small and compact search function to form this connectivity, which will resolve to something like this. So this column is node number, which are the nodes on contact surface. And for each node, I have two connecting elements. For example, for node 34, these are two elements that are connected to this one. And because this part of the code would be a little more time consuming, I've added this part to it. At first I skipped showing it to so if I have this connect element created already, I don't try to create it again. I will just use it. And if I have this connectivity or connect matrix formed, I won't do it again. Okay, now you know that how to search different things in your for example, IMP file, how to manipulate or deal with different matrices, and how to produce or make desired matrices out of what you have. And you know how to work and handle with allocatable matrices. So just as a reminder, allocatable matrices are the matrices that you don't know the size of them before dealing with them. And you just, so for example, this connect, I didn't know the size of it before starting to create it. So I just defined it as an allocatable matrix, which is gonna be this second rank tensor. But what's the size of it? When I know what the size of it should be, then I have used allocate to allocate the size of it to specify the size of this matrix. Okay, now I know the data over here, and I have formed the connectivity. So the other thing that I need to do, so far, I know, for example, this node is connected to these two elements. Now I need to find the yield strengths for these two integration points of these two elements. For doing that, there are a lot of ways to do this, but the way that I've used here is something like this. This is the yield strength at each point, and I have defined it to be a function of equivalent plastic strain and to be a function of pressure. Yeah, it's just a code. You can have different things. And I put it into a state variable. You don't need to put it in a state variable. You just need to assign it a number, a character, or anything. And then I have defined this matrix, YieldMe, which is the yield parameter that I'm going to use. And for the first component of this matrix, I have NOEL, I am within the UMAT, and NOEL, I have access to NOEL, which is the element. And the second component of each row of this matrix will be this state variable, which is the yield strength. So uh, YieldMe will give me the yield strengths at each element. Okay, so now I need to somehow share this matrix with the friction subroutine. So to do this, I am using this module function, module block. So I've defined a this YieldMe as a matrix, and I've shared it by using such thing. So this is the name of the module, and this is how you save this module. This module should be used within this subroutine. So if you have multiple subroutines and if you don't have use the name of the module, that module will not be used in that subroutine. And these are just the only things that will be shared between two subroutines. So for example, if you have something defined here, and let me scroll down to get to the freak. Okay, here is the freak. And for example, here, um, I have a component defined as this, for example. If I define this term or matrix or anything in the free matrix subroutine, and if I define it again in UMAT, but if I don't share it within these two subroutines, it will be two separate independent matrices. So, and so if you want to share something between different subroutines, just define it over here in the module and have this use module name into the subroutines that you want to use. And this should be just right below the name of the subroutine. There shouldn't be any space, any lines, written lines between these two. So, okay. And if you have something that you want to share between two different subroutines, you just need to define them in this module block. You should not define them within them. For example, I have defined YieldMe as a matrix in the module block. I cannot define it again here in UMAT or in the freak. Because if you do this, you can just try it. If you do this, it will not work. Point is how, okay, let me tell you how this module will work. It knows that YieldMe is going to be shared between these two subroutines, between UMAT and Preak. So whenever in any of these two subroutines that YieldMe is defined or is updated, it will be automatically updated for the other subroutine. For example, here, you know that I just showed you that YieldMe will be defined in UMAT based on when I have the yield strengths. So the second that you get this YieldMe into UMAT, at the same time you will have it in the freak. Okay, I think it is clear now enough. So, okay. So what I've done, let's summarize what I've done here. In the UMAT, I just opened up the INP file. I just made the connectivity, which is the node number, which is on the contact save, and two connecting elements to each node. Then in the UMAT, I have calculated the yield strengths, and I have assigned that yield strengths to a matrix named YieldMe, and this YieldMe is going to be shared using this module between the UMAT and the freak. Okay. So YieldMe will give me the yield strengths of each element. So for example, for this element, I know the yield strengths. For this element, I know the yield strengths. So in the freak, if I just find the node number, that it is just solving the freak for it, and it will be based on this node. if I can find, yeah. So for each node, when it tries to solve it, you need to use this connect matrix. And for example, you will see that it is working on node number 2. And based on this connect, connectivity matrix, you know that we need to know the yield strings of these two elements. So you will use YieldMe, and if I show it to you, I will use YieldMe of these two elements, and I will just use the average of these two and assign it to yield of that node. That freak subroutine is working on it. So let's uh, let's try to understand it better. Freak is working on a node, for example, node number 2. It comes to this point, and at first it opens up the connect, which is this connectivity matrix, and it will read it all from top to toe. So, and then it goes searches for this node number. It is working on this node. For example, let's say it is working on node number 9. So it starts searching this matrices. So if node is equal to connect, which is this one, I and 1, so it starts from 2. 9 is not equal to 2, then it goes to the second row until it gets to a line which has the same number. So then node is equal to 9. Now we know which line we are working on. And we know, based on this connectivity, we know the element number of connecting elements to this node. And thanks to this YieldMe, which is now shared to the freak subroutine, we know the yield strings of these two. And the average of the yield strings of these two elements will be assigned as the yield for this node. And this will be used in the remainder of this subroutine to do the calculation. This is the one of the most complicated ways, complicated features that we have in when we are dealing with different subroutines. If you want to share different parameters between two different subroutines, you can use call, you can use functions, but they are working with the same parameters. They are either for integration points or they are for nodes, which is somehow easier. But if you want to share data which are for integration points and nodes, yeah, it is a little more complicated. But now I hope that you know how to do it. So I hope that it was useful for you, and if you have any question, just come to our website and send us message. Thank you.